In today's video, I'm going to show you how to solve such problems on static equilibrium. Let's look at the problem. A rock and a meter stick balance at 0.25 meter mark, as shown in this diagram. The meter stick has a mass of 1 kilogram. What must be the mass of the rock? This is a problem on static equilibrium, and there are two conditions of static equilibrium. So the first condition is that the net force acting on this meter stick has to be 0. And this is Newton's second law. If the net force acting on an object is 0, what it means is that there's no translation in any direction. And for that matter, for this meter stick, if the net force acting on it is 0, then this meter stick is not moving up or down, left or right. And the second condition is that the net torque acting on this meter stick has to be 0. So this means that for this meter stick, we don't want any rotation about this pivot. We have to analyze the problem such that these two conditions are met. So we have a rock that is placed at the 0 meter mark, and then we have a pivot that is placed at the 0.25 meter mark, and then here would be the 0.50 meter mark. Then we are going to get the 0.75 meter mark and then 1.0 meter mark, because a meter stick is 100 centimeters long, and that is equal to 1 meter long. With this rock here, which we are going to determine the mass of this rock using the conditions of static equilibrium, the weight of this rock is going to act vertically downwards. So we call that WR as the weight of the rock, and that is equal to the mass of the rock, which is what we are going to find, times acceleration due to gravity. And if you look at this meter stick, we are assuming the 1 kilogram mass is uniformly distributed along the length of this meter stick. Therefore, the center of mass of this meter stick is going to be exactly at the 0.50 meter mark. And therefore, the total weight of the meter stick is going to act through the center of mass. And we can have the weight of this meter stick to be the mass of the meter stick times acceleration due to gravity. So let's check the first condition of static equilibrium, which is the translational equilibrium. So the net force either vertically along the y direction or horizontally along the x direction has to be equal to 0. So let's look at the vertical forces. So if you look at the net force along the y direction, which has to be equal to 0 for us to achieve translational equilibrium in the vertical direction, then we have the weight of this rock and also the weight due to the center of mass of this meter stick, all acting downwards. And then in support of these two forces, we do have the normal force which is exerted on the meter stick by the pivot points, and this normal force is going to be upward. So let's call it Fn. So if we do the Newton's second law for that, we are going to have Fn, which is the normal force supporting the weight of the rock as well as the weight of the meter stick through its center of mass, to be positive upwards, and then downwards we have minus the weight of the rock plus the weight of the meter stick, and that is equal to 0. So we can see that the normal force is equal to the weight of the rock plus the weight of the meter stick. And this condition tells us that the normal force is just equal to the total weight of the rock and the meter stick combined. Therefore, that gives a net acceleration of 0. So this meter stick is not going to accelerate up or down. It is going to be stationary in the vertical direction. In the same sense, in the horizontal direction, straight away, there's no acceleration because we don't have any horizontal forces acting on this meter stick. Therefore, the net force along the horizontal direction is 0. So that applies to the first condition of static equilibrium. Here we can see that translationally, this meter stick is in equilibrium because it is not moving up or down, left or right. Second condition to look at is the net torque. The net torque equals to 0 means that there shouldn't be any rotation about this pivot point. And let's look at that as well, which says that the net torque acting on this meter stick has to be equal to 0. And what is torque? Torque is defined as tau is equal to the vector r cross the vector f. So you can see that it is a cross product of the force F and some vector R. And we can express that as the magnitude of the vector R times the magnitude of the force and then sine of the angle between them. So if the angle between them is 90 degrees, that is they are perpendicular, sine of 90 is 1. So the torque becomes the magnitude of R times the magnitude of the force. So if we go back to our problem here, we can see that from the pivot, which is the 0 point in this case, we can define some R. From the pivot, we can define some R1. And at this point, we can see that there is the weight of this rock acting vertically downwards and they are perpendicular. So the angle between them is 90 degrees. Also, if you look at here, we can have R2 from the pivot. So we can define R2 and then that is also perpendicular to the weight of this meter stick through the center of mass. And since the angle is 90 degrees between them, we can define a torque which will set the meter stick to rotate clockwise. And the torque due to the weight of this rock is going to set the meter stick to rotate counterclockwise. And the second condition says that the sum of the clockwise and the counterclockwise torques has to be equal to 0. That is what this expression means. That means that the meter stick has to be in rotational equilibrium. We can define the torque due to the rock to be tau R, and that is equal to R1 times WR. And we can define the torque due to the weight of the meter stick, which is acting through the center of mass of the meter stick, as tau M, and that is going to be R2 WM. That is the weight of the meter stick. So the one due to the meter stick is clockwise, which is negative, and the one due to the rock is counterclockwise, which is positive. So if we do the net sum of these torques, is going to be tau R plus tau M equals 0. So we are going to have R1 mRg and then minus R2 mg, and that is equal to 0. Now, since we have this R1 mRg is equal to, we are moving all of this to cross the equal sign to the 0 side, so it becomes positive, right? So we will have R2 m and g. So we can see g on both sides, so we can cancel both out. So R1 mR is equal to R2 m. So we are looking for the mass of the rock, so we have mR. So we can divide both sides of this equation by R1. So this R1 cancels this R1 to 1, and then we are left with mR is going to be R2 times the mass of the meter stick divided by R1. And if we plug in these values, we are going to get R2. So R2 from the pivot is just 25 centimeters, which is 0.25 meters, right? So 0.25 meters times the mass of the meter stick, which is 1 kilogram. So 1 kilogram, and then divided by R1. So R1 is also 0 to the pivot, right? So that is 0.25 meters. So 0.25 meters. This 0.25 meters cancels this 0.25 meters, and we are left with the mass of the rock to be equal to 1 kilogram. And this is our answer. All right. I hope you enjoyed this. If you did, like, share, and also follow or subscribe to this channel. Until then, I'll see you on the next one. Bye-bye.